chapter and learn about another system or class of systems where quantum optics and condensed matter meet. And the field which I want to explain to you now is called optomechanics because it deals with how light couples to mechanical motion. Now, first of all, there are mechanical systems on the micron or nanoscale, and the typical thing to think of would be kind of beam or a cantilever that can vibrate. You would have, for example, a beam that is freely suspended between two parts of a substrate, and it could vibrate. Or you would have what is called a cantilever, which is attached to some substrate, and again, which can vibrate. And now, over the past 10 years or so, people have understood a variety of approaches of how to control these systems, how to couple to them, how to read out their motion. And the first kind of approach was actually to couple these to electrical circuits. So if you do that to nanomechanical systems, then you would call them nano-electromechanical systems. And there's even an abbreviation for this kind of system, namely they are called NEMs. It's not hard to imagine how that might work. For example, if you charge any of these beams and then you apply an electric field nearby and have a time-dependent electric field, then you can just drive the motion of this beam. In addition, if this beam then starts to vibrate, and for example it is part of an electrical circuit because it is metallic, then you might observe a change of its resistance or a change of the voltage applied to this beam, and so you could read out the motion. So that is one approach. And another approach that is more recent would be to couple these systems to the electromagnetic field in the optical domain. And I will explain later that typically this looks like having an optical cavity with some vibrating part which is driven by a laser. Now, before I start to talk about optomechanics in particular, I want to give a sort of overview of what are the goals of people who investigate nano or micro mechanical systems in general. And there are two different directions into which people go. One of them is more research into fundamental physics, especially if it comes to quantum effects, and the other is research into possible applications that involve, for example, sensitive detection. So let me write down a few notes for both of them. One of the goals that people have with regard to fundamental physics is to take one of these objects and place it into some non-classical state, for example into a superposition state, or entangle it with another quantum object. And the idea is simply the following, that these objects are so heavy, they are consisting of so many atoms, that this would test quantum mechanics in an entirely new regime. Now, why would you want to test quantum mechanics in this regime of heavy masses? Well, the idea is that we all know that for really large objects, macroscopic objects, we don't need to talk about superpositions, we don't need to talk about quantum mechanics, we usually can apply classical physics. And the question is, how does this work? How do you have a gradual transition, or maybe an abrupt transition from the quantum world to the classical world, to the classical behavior that we observe? So there is a commonly accepted notion of how this works, because as you go to larger and larger objects, they couple just more and more strongly to the unavoidable fluctuations of the noisy environment. And so this would lead to decoherence, it would quickly destroy all the superpositions, and if the objects are large enough, you may not even be able to produce a superposition in the first place because it would decohere so quickly. So that is a process that is known as decoherence. And one of the goals would be to test how decoherence evolves for these heavy objects. And there are some speculations that if you go to really heavy objects, then additional mechanisms for decoherence might kick in. For example, there's a speculation by Roger Penrose, who speculates that since we do not yet have a consistent theory of quantum gravity, we might as well speculate that if you place a heavy object into a superposition of being at two places, then there is an additional decoherence rate induced by gravitation. And that could be tested, but it could be tested only if the objects are sufficiently heavy. So this is one of the reasons why people would prefer to be able to put these objects into a superposition, rather than just putting a single atom into a superposition of two places, which of course has been done, but which would not be susceptible to this mechanism because the decoherence rate would be so low that you can't possibly test it. Okay, so this is speculative, but it is clear that decoherence will play an important role for these objects, and so you learn more about decoherence if you investigate superpositions. And there is a possible applied side to quantum physics, which we discussed already, which would be quantum information processing. So how do these objects possibly come into the picture for quantum information processing? Well, you can already guess at this point that these are not two-level systems, they are harmonic oscillators. So they would rather take the role, say, of the microwave cavity that we discussed for coupling to superconducting qubits. And so one of the possibilities for exploiting these objects would be to store some quantum information inside these objects, just in the same manner that you could store quantum information, say photons, inside a microwave cavity, and to read it out later. And so when we talk about storing quantum information in them, there's also another possibility which has to do with transferring quantum information between different systems. So it will turn out, and we will discuss this, not only can you couple these systems to light, but you can also couple them to electrical circuits, in particular superconducting circuits, in particular superconducting qubits. And there's the possibility that you would have the information first in the superconducting qubit. You want to put it into the light field, but it is very hard to do that directly because you cannot easily couple the optical field to a superconducting circuit. Because at the optical frequencies you would simply destroy superconductivity if a photon is absorbed. This is far beyond the superconducting gap. So the idea would rather be to have a superconducting qubit, couple it to some mechanical system, and then couple this mechanical system to light, and thereby indirectly transfer the quantum information from the superconducting qubit to the photons. So that would be transfer. Now for all of these things, obviously you need to be able to look at quantum dynamics, and in order to have quantum dynamics, you need to be in or close to the quantum ground state of these objects. And we will discuss the typical scales of these objects and find that this is not so easy. So I should remark that the typical mechanical frequencies for these objects are in the range of, well, kilohertz up to gigahertz. And if you convert this into temperatures, you will see that typically, if you say h bar omega equals kBT, these are temperatures that are smaller than the 20 millikelvin that can conventionally be reached in the laboratory. So we will learn a method by which you can use laser cooling in order to reduce the effective temperature even below what you could reach in the laboratory usually. But this is an important issue, reaching the quantum ground state. Okay, so this is quantum physics, and it provides a motivation for many people in the field. But then there's another very important aspect which I mentioned already, which would be applications. And while for applications it's also good to reduce thermal fluctuations, you do not always need to go to the quantum ground state. There are many interesting applications that already work in the classical domain. So one application of mechanical devices in general is very sensitive detection, for example, of tiny forces. And this is in particular evident since cantilevers of this kind have conventionally been used, since over 20 years being used in atomic force microscopy. So there the idea is to use these cantilevers to scan across the surface of some material and to look at the surface of the material with atomic resolution. So you would try to detect forces or force gradients actually, because if you apply a force gradient to an oscillator, then this adds something to the spring constant of the oscillator, so it shifts the frequency, and it is very easy to detect frequency shifts of a good quality oscillator. So that is actually an approach that is taken in atomic force microscopy. Something else that you can detect in these systems is simply changes of mass. Imagine you have this cantilever, it has a given fixed spring constant, and now there's a slight change of mass. Evidently this again changes the resonance frequency, and that you can detect with very high precision. And that is really useful, for example, in chemical diagnostics, because you can place some molecules on the surface of the cantilever such that they only bind with other very specific molecules. So if you have a gas of molecules coming nearby, only a particular species of the molecules will bind to the surface of the cantilever and thereby change its mass. So you can use this really to detect different chemical species. And that is being done. That is one of the big applications of these cantilevers. And then finally, in order to find all this, to measure the forces or the masses or the force gradients, in the end you need to read out the motion. This is obvious. So you need to be able to detect sensitively the displacement of these mechanical objects. Okay, so this is one thing. And then it turns out that the interaction between these systems and, say, the light field automatically provides some nonlinearities. And whenever you have a dynamical system that has nonlinearities, then by proper driving, you can turn this, for example, into an amplifier. So you can amplify very small signals. And the application is obvious. If you are able already to detect a small signal, then you just feed it into the amplifier, and it's best to integrate this with the next component directly on the chip. So that would be signal amplification, and then more generally, you could maybe also store part of the signal or generally process it using these nonlinear effects. And the nice thing about having optical signals is that you can easily take them out from the chip. So optics is usually very clean. Now for all of this, you don't need to go to the quantum ground state, but for many of these applications it would be very useful to integrate everything on the chip rather than build these things on an optical table, which is sometimes the case. You want to integrate them all on the chip and nanofabricate these devices. And so what are some of the advantages of mechanical systems? Well, for example, you compare with microwave cavities that we discussed so far, because they are also an option to process or store quantum information. And you will find that these nanomechanical systems can be far smaller. We saw, for example, that the typical microwave resonator would have dimensions, well, of the microwave wavelength, and that is on the order of millimeter or centimeter, whereas these nanomechanical devices can support the same frequencies, say gigahertz frequencies, and be only a few micron large. So you can integrate just many, many more of them. And then also, if you want to store information for a long time, it would be good to have high quality factors, which means to have a very large ring down time of the oscillations, and this is also true in many of the devices, although this somehow depends on frequencies and the fabrication method and so on. And another nice thing is simply that these mechanical systems can be made to couple to almost anything. So they can be made to couple to light, to electrical circuits, in particular also to superconducting circuits and qubits. They can be made to couple to spins and a lot of other things, such as cold atoms. One of the disadvantages is mentioned up here already in terms of quantum applications. You want to reach the quantum ground state for these applications, and then at least those oscillators that have frequencies more in the megahertz regime tend to be hard, because even at the lowest temperatures that can be reached in the laboratory, they would still contain thousands of phonons and be classical, and so you have to put in extra work to cool them down. Okay, so let's start by discussing mechanical effects of light. And then we will see how to combine these things into a mechanical system. So the most obvious mechanical effect of light is certainly the radiation pressure force. the typical setup would be that you reflect photons from a mirror. So it's easy to find the momentum kick that is imparted to the mirror because the photon just changes direction. So you have to transfer twice the momentum of a single photon. So the momentum change of the mirror would be twice the momentum of a single photon. That would be h bar k in quantum notation, but you could also say it's the energy of the single photon divided by the speed of light, because the energy is mc squared. And so if you have a steady stream of photons, then the force is the rate of momentum change, delta p over t. And so that would be the number of photons impinging onto the mirror in a given time times this momentum change. And so the number of photons times the energy of a single photon would be the total energy divided by the time would be the power measured in watt. So that is the result that Maxwell's theory predicts. The radiation pressure force on a perfectly reflecting mirror would be twice the power divided by the speed of light. And now the speed of light is a very large number, so as a consequence, numerically, the radiation pressure force often turns out to be really small. And one example that one can give is just to estimate if you have the sunlight impinging on a square meter, then this would be 1 kilowatt. And so if you divide by the speed of light, which contains the 10 to the 8, you get 10 to the minus 5 newtons as a radiation pressure force for 1 square meter. And so that is really tiny. And that is why if you stand in the sun, you feel the heat and you see it's bright, but you're not blown away. Still, we will see that in these devices one can find means of really enhancing the force and making it the strongest force in these devices. Now, numerically, this was predicted by Maxwell in the 19th century, but it turned out to be quite difficult to measure this tiny force unambiguously. And this was first achieved about 100 years ago. So that was achieved independently at Dartmouth College in the US by Nichols et al. And at Moscow by Lebedev. So what they used was a device which you may have seen as a toy, which is a torsion pendulum with two of these surfaces, one of which has light reflected from it. And so the idea is then that the whole structure would start turning around. And the crucial thing is to distinguish the effects of radiation pressure from the effects of just heating the gas. And it turned out that in all the early experiments, even before 1900 they had done experiments, in all the early experiments these heating effects were the dominant effects. And it turns out that the explanation for these heating effects is incredibly complicated. So you somehow have to distinguish radiation pressure from these effects. And one way of doing this would be, well, brute force generate an extremely good vacuum. That is one way of doing it. The other way of doing it is to exploit the different time constants. Because if you start illuminating at some point, the radiation pressure force will act instantaneously. But heating up the gas will take some time. And so that force only comes into play after some time. And that can be used for distinguishing the two forces. Okay. So that's around the time when it was first demonstrated, and as I just mentioned, it's usually very tiny. Now, There is another force which is related, but at first sight appears differently, and that is called the dipole force, which also has many modern applications. So here it's important that you have some polarizable particle inside a field where the intensity of the field depends on position. And the easiest way of producing such a field would simply be to have a standing light wave. So you have two counter-propagating beams, they will form a standing light wave, so the intensity will just vary sinusoidally. And so what happens if you place an atom at some point in this light wave or any polarizable object? Well, what happens is that the electric field produces some polarization, some dipole moment. The dipole moment interacts with the field, and so the energy, so to speak, at each moment in time would be minus the dipole moment times the electric field. Yeah. But the dipole moment itself is proportional to the electric field, with some proportionality constant that is determined by the polarizability of the object at the particular frequency of the light wave. However, because the dipole moment is proportional to the electric field, you see that the total energy goes like the field squared, that is the intensity. And so that means whenever the sign indeed is negative, the particle will be dragged into the regions of higher intensity. The sign can change if the proportionality between dipole moment and electric field is such that dipole moment is no longer along the electric field but opposite to it, and that will depend on how the laser frequency lies with respect to the atomic transition frequency actually. But this is the situation when the laser frequency is below the atomic transition frequency. You can imagine the limit of having a very, very slow field, not even in the optical domain, even at smaller fields, and then you are basically in a static situation and you know that a polarizable object is dragged along the gradient of the intensity of the field into the regions of higher field intensity. So the atom would be dragged into the region of high E squared, high intensity. And that is true if the light field frequency is actually smaller than the atomic transition frequencies. And that situation is called red detuned. You can also produce a blue detuned lattice simply by changing the frequency of the light wave, and then the atom will be pushed towards the regions of lowest intensity. Now that is really used to trap polarizable particles and in particular atoms. So for atoms, these standing light waves are then called optical lattices. There are other applications, for example, instead of having a lattice, you could just have a focused laser beam and then the intensity would be highest in the focus of the laser beam, so polarizable particles would be dragged into the focus, and that is used, for example, in biophysics to drag around small spheres. And this application then would be called optical tweezers, so in German, a tweezers and a Pinzette. So I will start the description by just looking at a situation like this, but we will keep the description relatively general, and in the end we will find that even in situations where you would describe things as being produced by a dipole force, the same description can be applied. So in a sense, they are not completely disconnected from the system. So I now want to take one typical optomechanical system, and you will see that we arrive at a Hamiltonian that really is very general and can be applied to all kinds of different structures, even those that look completely different. So if you think back to our description of circuit QED, this would be now like writing down the James-Cummings Hamiltonian, but instead of going through all the details of deriving the various components, we will just write down the Hamiltonian, simply also because we acquired some experience in the circuit QED case already. So again, what we have is a mechanical system, and in this case I just want to imagine we have some cantilever. It carries some mirror, at least in the sketch that I produce here. The purpose of the mirror is obviously to reflect light. And now the essential trick is to boost all the effects by enclosing this in an optical cavity. I mean, this situation would give a small radiation pressure force. You would be able to observe the bending of the cantilever, but that's about it. There are much more interesting effects if you enclose this inside an optical cavity. An optical cavity means you have two mirrors. One of them, say, is fully reflecting, that is the end mirror. One of them is only partially reflecting, such that light can enter into the cavity, but can also exit the cavity. So you would have a laser beam coming in, and then some of the photons again would leave out of the cavity. So in the end, of course, an important variable will be the displacement of this mirror. Let's call it x, and then you can imagine that sometimes it will be important to relate this displacement to the overall length of the cavity. Let's call that L. Now let's try to write down the Hamiltonian just by guessing the essential components of the system. That would be like guessing in the circuit QED case that there's a microwave resonator. Let's just pick one of the modes, and let's say it's a harmonic oscillator with A dagger A being the number of photons, and let's then describe the qubit as our two-level system, and let's write down the simplest coupling term that we can write down. In the same manner, we can say know that an optical cavity contains an infinity of normal modes, modes of the electromagnetic field in this enclosure. But then again, the laser has some fixed frequency, and this frequency will be closest to one of the optical modes, so we focus on this particular optical mode. That makes life easier. So then, how do we write down the Hamiltonian of this particular optical mode? Well, first imagine that there is no displacement, then this optical mode would simply be a harmonic oscillator. The number of excitations would be the number of photons stored inside the cavity in this particular optical mode. And the energy would be obviously the energy of a single photon multiplied by the number of photons. So h bar times the optical frequency is the energy of a single photon. And then I want to multiply with the number of photons, but I leave open some space just to accommodate the coupling to mechanics later on. Okay. Now how does mechanics come into play? Well, if there is some finite displacement, then the length of the cavity changes. But we know that the optical resonances inside an optical cavity do depend on the length. The same would be true of the microwave resonator, but there usually you can't change the length. So because of this, if there is a displacement, the frequency changes. It turns out, and we will see this in a moment, that the frequency changes such that the relative change in frequency is given by the ratio between the displacement and the length of the cavity. And so we will have to add other terms in a moment, but let me just point out that x times a dagger a is the important coupling, the optomechanical coupling, some displacement coupled to the photon number. And now, whenever you have a Hamiltonian and you have a term that goes like x, then you can interpret it as being x times some force, or rather minus x times some force. And so here you could just simply read off the force, that is everything except for the x, and find the force and this is obviously the energy of a single photon times the number of photons divided by the length of the cavity. And that force, which is proportional to the number of circulating photons, is nothing but the radiation pressure force. This is what you would expect, that the radiation pressure force scales linearly with the intensity. This is what Maxwell predicts, and here we express the intensity in terms of the photon number. Okay, so that is the radiation pressure force. Now, apart from that, we have to describe the other component of the system, which is the mechanical component, the cantilever. And here the idea is that at least if the displacements are small, it certainly can be described as a harmonic oscillator. In fact, for all of the systems I know, this is an extremely good approximation. And so you would write down h bar times omega, the mechanical frequency, times the number of phonons, the mechanical excitations, and for those, let's use the operators b. B dagger b would be the number of phonons. Plus other terms, and I will comment on those in a minute. Now we already read off the force. There are a few further notes. So, first of all, you know how the displacement x is connected to the operators b of a harmonic oscillator. So it is essentially b plus b dagger, and the prefactor is just the width of the ground state. And the width of the ground state is determined once you know the mass and you know the frequency. Now, just to give an example of the relevant scales, this width of the mechanical ground state obviously depends on the mass and the frequency, but for typical devices that are being investigated nowadays, this can be on the order of 10 to the minus 15 meter, that is a femtometer, the diameter of a proton. So that is very tiny. Actually, this of course is the diameter of a proton, and thereby it is far less than the diameter of an atom. And so you could wonder, how can the surface of this mechanical structure be defined on the length scale of the diameter of a proton? Even though certainly the surface will not be completely smooth, and then there are thermal fluctuations, there are some defects in the surface and so on. And the answer is simply that you average over many, many atoms. So the laser spot, the beam, will cover a large area, and so you average over many atoms. And that's why it makes sense to talk about the diameter of a proton with respect to the overall motion of this cantilever, even though it would not make much sense to try to determine the position of a single atom inside the surface to this precision. So that is a funny point. Okay, now let's come back to this part about the optical frequency and its dependence on the position. You know that the optical frequency is simply the speed of light times k. But now if you quantize the modes inside the optical cavity, you find the discrete modes such that an integer number of half wavelengths fits inside the length of the cavity. And so it turns out that this is c times pi over L, the length of the cavity, times the mode number. That is how many of the half wavelengths fit inside the cavity. And so in particular this means, if I just want to find what is the change in optical frequency for a given change in length, then the derivative of 1 over L gives minus 1 over L squared. And so I can rewrite this in terms of the optical frequency itself and say this is minus the frequency divided by L. So then if I expand the optical frequency in terms of displacement, it's the bare optical frequency minus x times this ratio. Or in other words, the expression which I already wrote down. And of course, in general, if the displacements get larger, you could imagine that there is a more complicated dependence of the optical frequency on displacement. Also, you can deliberately produce structures where the dependence here, for example, starts like x squared, and they are very interesting in their own right. But in general, this would be simply the lowest order term in the Taylor expansion. Okay, so then another remark, what are these three dots? And what are the terms in the Hamiltonian that we are still missing? Well, the first thing is we somehow would have to plug in the laser drive. We won't do that now, but we will do that later. That's the laser drive, and then there are the dissipative terms. So for example, the photons inside the optical cavity, they couple to the outside world through this partially reflecting mirror. So there is some decay rate at which they decay out of the cavity, and that would have to be taken into account. And that is determined by the rate kappa at which they would leak out of the cavity. this rate will play a very important role in the following, because it sets one of the time scales of the problem. So that is the photons, they decay, but also the phonons will decay. The phonons will decay simply because, for example, this cantilever will be attached to some substrate, and so the vibrations of this beam, then they will radiate into the substrate and be lost. The energy is dissipated, very simply. Actually, this is formally identical to what happens to the photons. The photons leak out of the mirror, and then they are radiated away. Again, the phonons leak out of this localized vibrational mode, and then they are radiated away into the substrate. And that process, of course, we could call decay of phonons, but in the classical domain we would simply talk of a mechanical damping. So this Hamiltonian would have to contain the coupling to the substrate, to the bath, the reservoir of phonons. And again, the mechanical damping would be described by a damping rate, and this damping rate in the following I would always call gamma m. So that's the typical classical damping rate of our mechanical oscillator. It's the complete equivalent of the photon decay rate kappa. But there's one difference between the photons and the phonons, and the difference is, of course, the frequency. And because the photons have a frequency of 10 to the 15 Hertz, the reservoir to which they couple can be treated as zero temperature. So without the laser there would not be any photons. It's different for the phonons. They have megahertz or gigahertz frequencies, and so there are always thermal phonons around, at least a little bit. So that means not only is there radiation of phonons away into the substrate, but also from time to time a thermal phonon from the substrate will enter my cantilever. So while gamma m describes the strength of the coupling to the reservoir, I also need to specify what is the temperature of this reservoir, because that determines the thermal fluctuations that act back on my cantilever. So these are the two quantities which you always have to specify if you have weak coupling to a reservoir in thermal equilibrium. It's the coupling strength, here specified via the rate, and the temperature. Then I just want to note that we already said we pick one optical mode, that is, for example, the one in resonance with the laser. And we also pick one mechanical mode, which is something I haven't emphasized so far, but actually, just as for the optical cavity, there are infinitely many electromagnetic modes. Also for the cantilever, there will be infinitely many mechanical modes. So the fundamental mechanical mode is one in which I have simple vibrations of a beam that is fixed at one end. That would be a typical mode to consider. But then, of course, there are other modes. For example, the next order mode would have one node. Somehow looks like this. And there are many others. And so if you go up this sequence of mechanical modes, you would arrive at modes that have very small wavelengths that look like ripples on the cantilever. Actually, if you go high up in frequency, you would also have modes that I can't draw here that would correspond to sound waves that propagate in the bulk of the cantilever. And so these are really just phonons. They are small wavelength sound waves, and they always display thermal fluctuations, just like all the other mechanical modes. So there is no clear distinction between the, so to speak, macroscopic mechanical modes and the vibrations of the crystal lattice. It's all the same, only these are the lowest frequency modes. Now there was some good reason to pick one particular optical mode. The question is, which mechanical mode to pick? And there is no good answer to that. Actually, if you try to measure the displacement of the cantilever by focusing on one spot and then recording the reflected phase of the laser beam, you will see all these vibrations just superimposed in the same manner that if you look at the vibrations of a part of a molecule, you will see all the different frequencies of the normal modes of vibrations of the molecule. And so then here it's just a matter of taste to focus, say, on the frequency of one particular mode. And later we will see that features such as cooling depend on frequency relations, for example, of the detuning between laser drive and optical resonance frequency being equal to the mechanical mode, and in this sense then you can pick deliberately one particular mechanical mode simply by changing the detuning and making sure that you address this mechanical mode. But a priori, none of them is selected. All of them vibrate all the time in thermal equilibrium. Okay, are there questions about this simple setup? If not, then I would start just discussing the basic physics. Not yet with formulas, but just to discuss what we can expect. So what is the simplest thought experiment that you can look at when you have such an optomechanical system? I think it's just to try and see what happens if you slowly move the mechanical object. If you slowly move the mirror, what happens? For example, what happens to the light field? And since I first want to cover the situation where we really move very, very slowly, I will call it statics. Now, as you move along, at some point you will come in resonance with the incoming laser radiation, and then the cavity fills up with light, and so also the radiation pressure force will increase. So what I want to plot is the radiation pressure force, or equivalently the circulating light intensity, versus the displacement. Now, typically if you pick a random displacement, you will not be in resonance with the incoming laser radiation, which is fixed at some arbitrary frequency. So the intensity will be very small. And if you move along, at some point the optical resonance frequency will come into resonance with the incoming laser. So then you see the typical Fabry-Perot Lorentzian resonance line shape in the circulating intensity, and therefore also in the force as a function of position. And then if you move further, you get out of resonance again. But as you move further still, there will be another mode that comes into resonance with the incoming laser radiation. Yeah, because if you want to plot all the different optical frequencies of the various modes in the optical cavity versus the length of the cavity, all of them go like 1 over L, that's the formula we had. And so this looks like that. And then if you fix the laser frequency somewhere, you see that as you increase the length or change x, which is the same, you will come into resonance with the various modes. So after some while you see the next resonance, and so on. Now the spacing is such, of course, that there's lambda half between the different resonances. And let me introduce a piece of notation here. The width of these resonances, or rather the full width at half maximum, is given by, well, lambda half, that would be the distance, divided by some number, which is hopefully large to make the resonances narrow. And this number has a name, it is called the finesse. So that's a measure of the optical cavity and how reflective the mirror is. Okay, so this is the force as a function of position, a sequence of peaks. And now whenever you have a one-dimensional system and you can plot the force as a function of position, it's very easy to turn this force into a potential. Yeah? Just define the potential such that the force would be the negative gradient. So I want to have F equals minus the potential that belongs to the radiation field, d over dx. So now if I plot the radiation potential, the effective radiation potential, what does it look like? Well, whenever there is no force, it has to be horizontal. Then whenever there is a force and the force pushes to the right, positive x values, I just need to have a step-like around its step. And then there will be the next step for the next resonance, and again for the next resonance, and so on. So this would be the rather curious potential that is provided by the radiation pressure force. And then you have to imagine that the full mechanical motion, of course, also sees the standard restoring potential of the mechanical structure. So you would add to that a harmonic oscillator potential. So that would be m omega squared half x squared, the potential energy of my harmonic oscillator. And if this is a parabola, then you still have to add the staircase, and you'll find a rather curious behavior. Namely, you see that at some places there are local minima, and there can be several of those, depending on the strength of this extra potential. And so the local minima of the overall potential that is seen by the mechanical system, of course, they correspond to stable equilibrium positions. So depending on the history of the system, it can sit in either of these local minima. They correspond to situations where the radiation pressure force exactly balances the restoring force by the usual mechanical spring. Sometimes there is almost no light, so the radiation pressure force is small and the restoring force also has to be small, so the displacement from the usual equilibrium position will be small. But sometimes there's a lot of light in the cavity and then the displacement will be large. And so whenever you have a system that has several stable equilibrium positions, you can find out that this is indeed the case by doing simple experiments where you just change some parameter and look at the output of the system. Because what will happen, for example, if you change the light intensity, which means changing the strength of this extra potential, or you change other parameters, is that you move the system around and for some time it just will track one of the local minima, but then suddenly it will roll into another local minimum. And if you then change the parameter back again, it may stay in this other local minimum. So what you get is some kind of hysteresis, because there's more than one equilibrium position. And so that is something which people even tried in the 80s, not yet with these nano or micromechanical systems, but with a rather heavy mirror. And what they observed was then something like, if they change the incoming laser intensity and they plot the outgoing light intensity in their particular structure, then they would see that if they sweep one direction, they see something like this, and if they sweep another direction, they see a jump at a different point. So the message is that you can observe hysteresis in a system like this. Okay. There's another consequence of adding this potential, and that is the following. You look at the curvature of the original potential, and it is defined by the spring constant, or the mass and the frequency, which is the same. Now, since you added this light potential, the curvature at the place of the local minimum, at the place of the equilibrium position, also changes. So you might start talking of an effective spring constant that has been changed by the light field. And that is indeed true, and this effect is called optical spring effect. And it turns out there are systems in which this optical spring effect can be, say, a factor of 100 stronger than the intrinsic mechanical spring. So it can be really stiff, a very strong effect. Okay. So much about statics, which is we always imagine that for each position we give enough time for the system to settle into this new state, and in particular for the light intensity to adapt to the new length of the cavity. The idea now is to relax this assumption and go to situations where the cantilever or the mechanical structure just moves around at a finite speed, and so because it moves around, somehow the light intensity doesn't have the required time to completely track the mechanical motion, and that means we will have time lag effects. Okay, so let's talk about the dynamics in these systems. And the situation I want to imagine is the one I had previously, again we plot the force versus position, and if we sweep along adiabatically, that is basically at zero speed, then we just see the usual Lorentzian line shape. But now we imagine that we sweep along at finite speed. Again, the axis is not time, but the position that I have reached. I sweep along at finite speed, which means if I have reached this position, then the intensity has not yet built up to its full value, so I will observe a smaller intensity, a smaller force. And again, once I reach this position, the intensity has not yet relaxed down to the small value, but it has retained a memory of having been larger before. So what I see is sort of displaced curve like this. So that is for finite speed. So there is a time lag between the motion and the observed intensity. And the time lag, the time scale for this is of course given by the cavity ring down rate, by kappa, the time it needs for photons to leak out or also to somehow enter the cavity and fill the cavity. Kappa is the rate, and then of course the time lag would be set by the inverse kappa. Now whether this is important or not depends of course on numbers, but the typical ring down times of photons in the cavities that are being used are, say, on the order of microseconds. And now if the typical frequencies of the dynamics are also on the order of megahertz, that is inverse microseconds, you can already guess that these can become comparable, and so this is an important effect. And now, whenever you have a situation like this, it just means that the force is no longer simply a function of the position at this given instant of time. In the static case it was. Here it is no longer, but rather we have a situation where the force at a given time depends on the full prehistory in principle of the motion of x, because that determines how the light field builds up and depletes again. So the situation now becomes more complicated, and in particular it also becomes more interesting because this force is no longer a conservative force. I can no longer simply write down a potential. And if I can't write down a potential, there's also the option that, for example, this force generates some friction. So that's something qualitatively different from before. So let's try to figure out qualitatively the consequences of this. What I want to imagine now is that we take this resonance curve and we place the mechanical system somewhere in an equilibrium position, somewhere here. And then we ask what happens if it moves a little bit. And we want to find that indeed this force can lead to friction, for example. So again, I plot this resonance. I plot the curve for the adiabatic case. And now I want to imagine that in equilibrium we have placed our cantilever or our mirror such that, for example, it sits here somewhere on the rising slope of the resonance. So that would be the equilibrium position. Now, at this position, of course, it feels some average force, but that is not really important at the moment. What we want to look at is the following. You know that even in thermal equilibrium, a harmonic oscillator always executes some oscillations. the amplitude of these oscillations, it changes in time. You can calculate the amplitude if you know the temperature and the spring constant, but this is how it looks like. And now I just want to follow what happens during one such cycle of oscillation, say from here to here. So I essentially just go back to the same position. This line, by the way, would be the equilibrium position, and then we have these oscillations around the equilibrium position. So what happens? Well, the point is that as I approach the resonance, the force or the intensity will be a little bit smaller than expected in the adiabatic case because of the time lag. Yeah? So this part of my trajectory in the fx plane might look like this. Force is a little bit smaller than expected because it still has to build up. But then as I go back, and I have already reached a higher intensity, the intensity for some time will remain high. So the force will remain higher than expected in the adiabatic case. So that's the second half of the cycle. So as a consequence, the force acting in the two halves of the cycle will not be identical in magnitude. Will not be identical. And so as a consequence, I can calculate the work done by the radiation pressure force in such a cycle, and I will find it's non-zero, because that's just the area in this curve. It's non-zero, and if you work it out in this case and take into account the direction of the force, you will find it's negative. Because in the second half of the cycle, when we were moving away from the resonance, and so the motion was against the force was relatively strong. It was stronger than before. And so if you move against the force, you lose the work. Okay, so what does that mean? That means the light field, the force provided by the light field, really extracts energy from my mechanical motion. And if this happens, you can call it a kind of extra damping. So this is some damping induced by the light field. So you could say gamma, the overall damping rate of my mechanical system, would consist of the intrinsic damping rate that we discussed briefly. That is a consequence of the mechanical structure and so on, plus an extra term that is induced by the light field. That would be the optomechanical damping rate. And of course, one of the things that we will have to discuss is how does this optomechanical damping rate depend on the parameters, because that is one of the important effects that are observed in these structures. Now, whenever there is extra damping, but no extra fluctuations, then this damping can simply be used to damp away the thermal fluctuations. Thermal fluctuations always arise as an equilibrium between the damping that wants to extract energy and the thermal force, the random force that comes in from the outside and tries to heat up the system. So in thermal equilibrium you have a balance between the two. And now if you change something with the damping and increase the damping, but you don't increase the fluctuations, then effectively you will reduce the fluctuations, and so you will reduce the effective temperature. And that, of course, is good news, because I already told you that for many of these structures, the typical, say, dilution refrigerators that people have available in the laboratory would not be good enough to cool them down to the quantum ground state. So the idea then is to use this extra damping mechanism, the light-induced damping mechanism, to cool them down even further. Okay. So I remarked that we were looking at the situation on the rising slope of the resonance. Let's have a second look at this situation with respect to the frequencies. So in this situation, the cavity is rather short as compared to the situation for the resonance. Yeah. And if the cavity is short, we already remarked that this means we have a rather high optical frequency, resonance frequency of the optical mode. So in this situation, actually the optical frequency turns out to be larger than the laser frequency. In other words, the laser is red detuned. And now in the following, I always want to quantify where is my laser with respect to the optical resonance, and so I will introduce what we call the detuning. So here I want to define this as delta equals the laser frequency minus the optical resonance frequency. And so in the case we have here, that would be negative. So at negative detuning, this is our convention, at negative detuning we have a red detuned situation, so we get cooling. Now, you can try to go through the same argument at the other side of the resonance. And interestingly, you'll find that the sign is reversed. The sign is simply reversed, and if you express this in terms of an extra damping rate, this turns out to be negative. So negative extra damping. Now, in the first moment, this just means that the overall damping rate is reduced. If you reduce the damping rate, but you don't reduce the incoming thermal fluctuations from the environment, then effectively this heats up your fluctuations because there's not enough damping to damp them away. So that means at first this means extra heating. The effective temperature of your mechanical mode will be increased. And we will discuss all of this in more quantitative detail, but this is the quantitative discussion. Now, there's an interesting situation when you try to increase ever further the magnitude of this extra light-induced damping rate, simply by increasing the laser intensity, because that scales with the laser intensity. Because then, since this is negative, at some point, the overall damping rate will become negative. So the question is, what happens then? Well, that just means the following. If I look at the time evolution of my mechanical system, say it starts at its nominal equilibrium position, but then there will always be tiny oscillations, for example in thermal equilibrium. And now because of the negative damping, instead of being damped away, these tiny fluctuations will simply blow up exponentially in time. And so the exponential blow-up is simply given by e to the minus gamma t. That would be the law that obtains, so there would be 1/2 in here if I look at the amplitude. That would be the law that obtains in general, but now gamma is negative, so it corresponds to an exponential explosion. Now that doesn't go on forever, otherwise the mechanical system would break. But even before that happens, some nonlinear effects kick in, because before that happens, at some point, for example, the motion becomes so large that the amplitude gets out of the range of the slope, and then the motion saturates. And one of the questions you can ask is, obviously, what is the value of this amplitude that the system saturates to? Now these oscillations, they are called self-induced oscillations. Because somehow they do not arise from external forcing. There is no resonant force applied. In particular, this also means that the phase of these oscillations is completely undetermined. Just depends on the random fluctuations that were there in the beginning and then they lower. The funny remark is that this situation is exactly analogous to what happens in a laser. So in a laser you pump, which means just supply incoherently some energy by various means, electrical discharges or another light source, and then the laser somehow is able to feed all of the supply of energy into its coherent oscillation. And the same happens here. The system obtains a supply of energy, that is the incoming optical radiation, and it is able to feed that energy into coherent mechanical oscillations. Fine, so we learned something about the statics. When things move very slowly, then we learned something about how the dynamics is changed by the light-induced forces. But before someone can analyze all of this, one simply has to be able to look at the system. One has to be able to look at the dynamics to follow x of t. Now I want to say a word about this. Of course, basically the principle is very simple because you already have an interferometer. You have your optical cavity, that is an interferometer. And so you should be able to read out the displacement. Okay, so what's the basic principle? You simply have these two mirrors, one of them can move, and you send in a laser and you look at the back reflected signal. Now if the end mirror is really perfectly reflecting, then obviously all of the intensity that you send in also has to come back. So all the amount of freedom that you have in the system is contained in adding a phase shift to the reflected light. And so then what people look at obviously is this reflection phase shift as a function of position. Now, you can work that out, and we will maybe do that, but the general quantitative behavior is simple to understand. If I'm away from the resonance, my phase shift really doesn't change as a function of position. Because, for example, if I'm below the resonance, or if I'm away from the resonance, light does not even enter the cavity. It's just as if I were reflecting from the initial mirror. And so it won't even feel the displacement. But right at the resonance, there is some change in the phase shift. And I go through the resonance. And so it is obvious that it is in this region that I should measure the phase shift in order to learn something about my displacement. Now one can work out how the phase shift does depend on position. And it's given by 4 times the optical frequency divided by kappa times x over f. So again, it seems to be important what is the fraction of the displacement versus the cavity length. That is somehow reasonable. And also, the phase shift will be larger if kappa is smaller. Because if kappa, the photon decay rate, is smaller, then the resonance is sharper. If the resonance is sharper, then I just get a steeper slope here. And if I have a steeper slope, then a small tiny displacement translates into a large phase shift. Now, in order just to give you a number, for typical setups, this phase shift could be, say, on the order of 1 if I have a displacement of a picometer. So actually this would be true for an optical cavity with a finesse of about 1 million, because I already told you that the width of these resonance peaks is the wavelength divided by the finesse. And so the wavelength is micron for optical radiation divided by 1 million is picometer. So that is fairly sensitive. Now, what does one observe if one takes the reflection phase shift and, say, tries to figure out the displacement as a function of time? Well, this is a picture which I already sketched. What is the time evolution of the position of a harmonic oscillator in thermal equilibrium? It oscillates at its eigenfrequency, but the amplitude slowly fluctuates in the course of time. And it does so on a time scale that is set by the damping rate. So this is one damping time. So the idea is that when the amplitude rises, this is because thermal fluctuations from the outside heat up the motion and provide some extra energy, but then maybe the thermal fluctuations get weaker and there is the remaining damping that depletes the energy. And so there are fluctuations all the time, and the question is now, how large is the variance of the fluctuations? So what is the average of x squared, if I imagine my average x to be 0? Well, that is not so difficult. You know that for a harmonic oscillator, if you apply statistical physics, if you apply the Boltzmann distribution, things are very simple. In particular, whenever you have a Hamiltonian that only contains terms that are quadratic in the variables like x or p, then you have what is called the equipartition theorem. So that would tell you that the average potential energy, and that would be m omega squared x squared half, the average potential energy is equal kBt half. And so as a consequence, the variance of x is directly given by the thermal energy divided by m omega squared. So for our fluctuations, this means that the amplitude of these fluctuations, which should be the square root of the variance, goes like the square root of the temperature. And that is one obvious way to extract temperature. we will continue next time at this point, but the crucial feature is that if you really were to look at the phase shift as a function of time, you would see a far more complicated pattern than here. And the real reason for that is that there is not only one normal mode in the mechanical structure, there is an infinity of normal modes, and so the displacement of this end mirror at the position of the laser spot would be a superposition of all these normal mode vibrations that consist of different frequencies. So you would have a rather complicated pattern here, and then you want to Fourier decompose it. And so it's better just to look at the spectrum and the Fourier decomposition. Okay, are there any remaining questions? No? Okay, so thank you.